Hello. Um, Hopefully you guys can see the last part of that part one because someone jumped onto my Zoom meeting, which is really weird because I know her, but I don't know how the hell she got on my Zoom meeting. But anyways, let's get started with part two. Okay, so um, last chapter, last part, we ended with adaptive um, and harmonic resistance and stuff. So okay, so let's talk more about natural selection. Okay, what natural selection actually does, okay, is eliminate bad alleles. Okay, so um, if you're weak, if you're if you're struggling in any way, natural selection will eliminate for the adaptive phenotypes. So like honestly, I would if it wasn't for medical science, I wouldn't be here teaching you guys biology today. I'm fat, I'm slow. I had a heart issue before, my eyes suck. So like, in the wild, I'll be next to useless. Um, Actually, I'll be more than useless. I'll be a complete negative. Okay. But okay, so as environmental conditions change, the phenotypes that natural selection favors will change too. Okay, so adaptations that seem perfect in one environment will be completely wrong in another environment. The best example of that, polar bears. Okay, polar bears are great right now. They're living in the Arctic. They've lived there for thousands of years at least, hunting wild animals in the Arctic, and they're white. They're big. Their fur is white. They have adaptations like big paws that allow them to swim. They put on a lot of fat that keeps them warm. But all of that is going to disappear eventually when the Earth warms up, right, global warming, to where the Arctic melts during summer, and then they have no place to go. And so, polar bears are not really. I mean, I don't see polar bears surviving another 100 years in the wild. Okay, so enjoy them now, because eventually you'll only see them in the zoo. Okay. Okay. Natural selection can eliminate some entire species, like these sea scorpions. This is fossil, and these type of trees are no longer there. Okay. Okay. So this is another fallacy that people have. Evolution does not have an end goal. Humans are not the end goal of evolution. Um, so there is no goal. Okay, there's only survival in the now. There's no end goal. There's no like, we need wings in the future, so grow wings now. That's not how evolution occurs. Okay. Okay. All right. Um, okay. So the orchid and the wasp pollinator have evolved to be alongside one another. It's something called co-evolution. The orchid does not have to evolve in order to be better populated. That just created a selective advantage. Okay. Okay. Fitness is reproductive success. Okay. So people get confused what survival of the fitness is. Okay. People think like survival of the fittest, stronger, bigger, faster, better. None of that is actually survival of the fitness. Survival of the fitness is the ability to reproduce. Okay. Um, Fitness depends on ability to reproduce the organism's next generation. Okay. Okay. So let's try that one. Okay. So okay. So B and C are both correct. Okay. So how can natural selection favor different phenotypes at different times? Make sure you can answer that question because that will show up on the quiz. Okay. Okay. Evolution is not only possible, it is unavoidable. In real populations, allelic frequencies will inevitably change over time because there's so many different forces that select them one way or another. Every single generation is going to be different than every other generation. The changes might be small, it might not be noticeable, but they are there and you can test for them. Okay. Okay. So what scientists test for when they study, when they test evolution, is they measure something called Hardy-Weinberg equilibrium. Okay, so let's talk about what this is. Okay, so in this hypothetical population of ferrets, the allele D produces big D, or capital D produces dark fur, and lowercase d produces light fur. Okay, and count the number of alleles, you can calculate the frequency of the allele. Okay, so let's open a whiteboard and then we can see what that is. Okay, so whiteboard. Okay. So first thing I'm going to do is assume there are 200 ferrets. Okay, each ferret has 2 alleles. Therefore, there are 200 alleles in the population. Okay. Okay, so let's go back to this. Okay, so it can be compared to real populations to see if something is happening. Okay, so okay, we can calculate the allele and the genotype frequencies. Okay, we can't see the alleles, but we can see the genotype frequencies. Actually, we can't see all the genotype frequencies, but we can see one particular genotype frequency. Okay, so okay, let's assume we have 10 light colored ferrets. Okay, each light color ferret has to be okay. Now, so some definitions. Okay, so P squared is the frequency. Okay, so let me see. So P is equal to the frequency of the dominant allele. Okay, Q is equal to the frequency of the recessive. Okay, so there's only two alleles in the population. So the frequency of the dominant allele and the frequency of the recessive allele. So P plus Q has to equal 1. Okay. So if you have P, that's the frequency of an allele. So if you're an individual with 2 P's, okay, so that is P squared. Okay, so P squared is equal to the frequency of the homozygous dominant. Okay, so Q, actually I'm gonna make all these lowercase q. Q squared is the frequency of the homozygous recessive. Okay, PQ is equal to the frequency of the hetero. There's 2. So you can have a dominant and recessive dominant. So, okay. So since P and Q are equal, so 2 plus 2 PQ. Sorry, all the capital P's in the right place. Okay, so okay, 2PQ is the frequency of the heterozygous. Okay, this part you do need a calculator for, so let's go through. Okay. So we have 10 light colored ferrets, okay, out of 100. Okay, so 10 out of 100 is equal to allele or Q. Okay, so 10 out of 100 is Q squared. Okay, if 10 out of 100 is Q squared, uh-oh. Q is equal to 31. Okay. Okay. Or 31.6%. Okay. So I can take the square root of 0.1. The square root of 0.1 is 3.16. Okay. So P plus Q is equal to 1. Okay. Therefore, P is equal to 1 minus 3.16. And that equals to 0.68. Okay. So just to reiterate, Q is equal to 0.316. P is equal to 0.684. So Q squared is equal to 0.1. P squared is equal to 0.684 times 0.684. Point 0.46. And then 2PQ, 2PQ, 2 times 2 times 0.684 times 3.316. Okay, so Q squared equals to 0.01, P squared equals to 0.46, and then PQ equals to 0.3432. Okay, so in other words, to talk to people, homosexual colors, these are going to be the homozygous recessive. This is going to be a homozygous dominant. And they're going to be heterozygous. Okay, I want you guys to listen to this first, and then we'll go over examples of this in class on Wednesday. Okay. 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 So we'll go through this combination on this question on Wednesday. So okay. Natural selection can shape populations. Okay, so directional selection is evolution over time, constantly selecting one side over the other. So it shifts in that direction. So in this example, the darker tree color, okay, allows the darker tree moths to constantly survive better than the lighter ones. And eventually over time, the light moth population will die out or become very little compared to the dark moth population. Okay. We'll explain stabilizing selection first. Stabilizing selection selects for the intermediate phenotype, the one in the middle, like the middle-sized baby in this case. Okay. So smaller babies have different health issues. Okay, because they're too small. Larger babies have a hard time coming out of the mother, So they have some issues coming out. If you're in the middle, then you're at the best of both worlds. Okay. Okay. All right. So, that's another thing. Disruptive selection. Disruptive selection, you select against the middle. You survive, you select for the edges. Okay. So walking on the right side of the street is good. Walking on the left side is good. Walking in the middle gets you run over by a car. So like there's benefits to either side, but not the middle. Okay. Okay, we'll skip the harmful alleles. Heterozygote advantage. Okay. The heterozygote advantage really is simple. There's an advantage to being a heterozygote, okay, of some sort. Okay. Okay. Sexual selection directly influences reproductive success. The best example of sexual selection is peacocks. Okay, peacocks. First of all, peacocks are males. Peahens are female. I'm sure all of you guys have heard of peacocks, but not all of you guys have heard of peahens, and that's sexual selection. Okay, so the peacock, okay, has a very large tail that's really brightly colored. The male itself is really brightly colored. Neither of that is good for survival. Okay, it makes them harder to run away from predators, makes them shiny and therefore easy to see. So that's usually not good for survival. But it tells the female that, hey, this male is still alive, even though it has all these traits. The other genes in this female or the other genes in this male must be really, really good. Therefore, I'm gonna go allow him to have sex with me, and I'm gonna have his children because the children will be more likely to survive. Okay, and that is sexual selection. Okay. Okay. So sexual selection results from variation to an ability to obtain mates. Okay. And that's why you see things like peacocks. A lot of male birds are showy and the females are kind of dull. And the same in fish, right? The guppies, they're all the right colored ones are all male. Okay. Okay, so that term is called sexual selection. Okay, so individuals with the sexually selected traits mate the most and pass on their genes the most. So mating is not random. Okay, Hardy-Weinberg evolution does not occur. So for Hardy-Weinberg, certain things have to be true. Okay, for Hardy-Weinberg equilibrium, okay, the allele frequencies stay the same. There should be no natural selection. Okay, there should be random mating, no migration, no genetic drift, no mutation, no natural selection. Okay. Okay. So what else? Mutations cause evolution to occur because mutations select for greater genetic diversity. There's always a mutation. So Hardy-Weinberg is never true. Okay. Sampling drift. Drift is sampling error. Okay. The drift causes evolution to occur. Drift occurs in small populations. It doesn't really occur that much in larger populations. But you know, so like 10% of the population is left-handed. Okay, and now in a large population, that will roughly be true. But if you randomly pick like 5 people, like there's a chance that 2 of them are left-handed, and 2 of them are left-handed, and if they're the only ones who reproduce, then the next generation after that, 40% will be left-handed. So that changes the allele frequency over time. Okay, this process is called founder effect. Founder effect causes genetic drift. Okay, as this population bottlenecking. Okay, population bottlenecking. Okay, causes genetic drift because the population bottleneck occurs if you pour only a few marbles out of this bottle, you lose the yellow ones, you lose the green ones, the other ones become like there's now a lot more reds and blues than there used to be. And you know, the ratios are different. Okay. So this occurs in cheetah. This is something that occurred in a cheetah population. Okay. So in a cheetah population, there was a time when there's very, very, very few cheetahs. Okay, so much so that the cheetah genome became really, 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 really small, and there's not a lot of differences between cheetahs. If you pick any 2 cheetahs from the wild, they are more closely related to each other than any 2 male siblings. Okay, or human siblings. Okay, they're that close to each other. Okay. Okay, non-random mating causes evolution to occur. There's always going to be a fight for mates. Mating is rarely random. Okay, so you know, you mate for whoever you want to. Okay, gene flow also causes evolution to occur. Gene flow is when members of a population move one population to another one, and that changes the frequency of not only the first population that left, but it changes the frequency of the second population in which it joined. Okay, all right, hopefully that makes sense to you guys. I will try to explain all of this on Wednesday. I will see you all then.